Yeah.
Okay, so the whole thing I want to do today is that everything probably seemed quite abstract up to now. And so we want to try and make things slightly less abstract. And we've reached kind of an interesting watershed in the course where we've been building up towards, through sensors and analog processing, to instrumentation and biopotential measurement. And then on the other side of this, from here on in, starting probably Thursday, we'll start looking at kind of the digital side. Once we've acquired the signal, once we have it on a computer, and how we can process it to extract information. But today, let's just see these ideas of like the biopotential measurement and the electrodes and so on, just all kind of coming together. So I should point out, for the first thing I wanted to point out was instrumentation amplifiers that we had looked at. We started to build them with fundamentals using op-amp design. Usually you buy them as if I was going to build a little device for, say, measuring ECG or something, a little Holter monitor, I would use instrumentation amplifiers not unlike these guys here. So for example, here's an analog device, it's an AD620, it's a great little instrumentation amplifier. Some more analog devices, instrumentation amplifiers. This Burr Brown INA 101, it's a great little building block for building, say, ECG amp. Remember, good common mode rejection ratio, I think it's about 90 dB common mode rejection ratio, it's good. So, don't pass them around, don't try not to lose them. Okay, so that's instrumentation amplifier, that'll do some basic measurement. But ultimately, when one is, well, we're only going to be looking at research kind of instruments here. But generally, there's a lot more kind of glue circuitry, filtering and associated processing in order to come up with a higher performance biopotential measurement system, as we saw. And so our platform we use for maybe talking about such instruments is this BioPack system here. It's basically a research and teaching physiological signal acquisition system. We don't actually use this for our research because we have even better systems again that have better performance, but too large and cumbersome to bring up here. But essentially, this BioPack system is basically a data acquisition system, right? So basically, it'll sample signals, analog signals at high data rates, and stream them onto the computer for storage. And it comes with a whole bundle of amplifiers, which is connected to its instrumentation interface that it will sample from and drive. Okay? So, nearly all these here, each of these is an amplifier, a biopotential amplifier, most of them, except for these two. This is EMG amplifier, an evoked potential amplifier, an ECG amplifier, an evoked potential amplifier. Well, and this is the galvanic skin response amplifier, and then there's another evoked potential amplifier. Evoked potential amplifiers are essentially amplifiers you would use for measuring EEG. Before I go into the BioPack, I'll point out one other thing. When we're doing EEG measurements, i.e. signals measured from the brain, what's important there is that we're measuring from many different sites on the head, generally at least 16 or 32. This is an electrode cap, which we saw before, didn't we? Didn't we? I brought passed it around in one other lecture, didn't we? I don't know. No, maybe not. Oh, was that a glow? Okay, so here's the cap. It's all got these electrodes at certain positions, and here's the classic image you might have seen in somewhere. Yeah? An EEG. This is the classic EEG measurement. Right, so pass around. So basically, the electrodes are integrated here. They're little ring electrodes, and there's a little hole in them. And the little holes in there because that's where we have to inject gel with a syringe in order to make the contact with the tissue. And then they're all bussed back here. And they come with there's all your electrode connections there. because with the EEG you're measuring a whole lot of channels at the same time, generally 32 or so, it doesn't come in, you know, we don't have 32 little amplifiers like this. We could do, it'd be cumbersome. This is kind of structure or in the form of an EEG amplifier. There's something like this. This is kind of a rack mounted one. It could be rack mounted. It's a little bit of attachment to that. But so each of these is generally kind of a bipolar measurement. Okay, but there's various montages that we kind of alluded to the last day in how you connect up the electrodes, how you do the difference measurement, or how you create a reference measurement and so on. So that's just in a way, you could build this from a whole bunch of these. It's a bit more to it than that, because a little bit more to that, just purely because of the performance you need, i.e. very high gain, but very high combo rejection ratio, even more important. Required that you might be, I mean, I don't know exactly how these neuropulse amplifiers work. There might be some chopping kind of circuitry going on where it kind of modulates the signal up into cleaner spectrum before it passes a digital amplifier in a cleaner passband before applying the gain, right? But this is what they look like. And this particular one has a SCSI interface that talks to generally any computer with a SCSI adapter. SCSI is kind of old school, so we don't really use this amplifier anymore. Even though there's a final project student working on it this year, in which Dawn will be trying to this comes with a piece of software, not like this software here for actually doing data acquisition. And yeah, hi Darren. I haven't tried it yet. Will you sit in here a minute? Yeah. Just in case I don't use it anymore. Okay. Good, you can be there. You need some measurements on, yeah. Great. So Darren's doing a PhD in what was the Tal Hospital for stroke rehabilitation, and in fact Darren's final project, not like Dawn's, was to use this amplifier here to measure. Was it this amplifier? Yeah. Yeah. Oh, yeah, it was it? Yeah. Yeah, to measure EEG over the supplementary motor area. Somebody might have had that as one of their Broadman areas. Somebody definitely did. Who was it? It was you, wasn't it? Yeah. So Darren was measuring over the supplementary motor area, which is associated with motor planning. And so one expects to see during engagement in a motor planning exercise, modulation in the relative powers of the EEG in two critical kind of bands, or two standard bands, beta and alpha band. Okay? So Darren was looking to see if he could pick up that signal and then use it to drive some communication software. Okay, so it was a brain-computer interface based on motor planning activity. If it saw it, triggered, flashed to light, and you could use that for something. Or as it turns out, this is why Darren's PhD is kind of in this related area, is if you've got a signal there that's associated with motor planning, you can maybe harness it for biofeedback purposes in rehabilitation. But so this is your cap. They all plug in back there, and then you have some software to do the data acquisition. So you just have a look at that point, push that around, and watch out. Don't let any electrodes catch on it. This is very expensive. Don't let anything catch on anything, all right? No. Like that cap is without the leads is about 400 euros, isn't it? Yeah. It's just a cap. There's a business for somebody there. Well, it's got electrodes integrated into it. But also, remember the last day I said it's very important to get the skin impedances down because we're losing signal across that, yeah? So we might often use it with, well, that particular system there, there's no, you need to test, you put on the cap first, gel it up, before you plug it in here. I guess, Darren, you've used this, haven't you? Yeah. Yeah, so you plug it in here and you can go through each set of pins here and determine the impedance you're seeing. Okay, so you want to get them fairly low, right? About 20 kilo and fairly uniform if you can. Having said that, there's a good paper I just read this year that's basically stating that with the quality of the very good EEG amps you have now, you don't need to get it below 20 kilo ohms so much. Okay? The reason that might be an issue is that when you're actually, to get the